Here we're going to look at one example of graphing a function with transformations. And so let's say we want to graph the function f of x equals 2 times the quantity x minus 3 squared plus 1. Well, the first thing we would want to do, the whole strategy is to boil this down to a simple function, a parent function. Like, in this case, let's deal with the parent function y equals x squared. This function is based on this parent. And then what we want to do is take into account the arithmetic that we see here. You know, this minus 3, the times 2, the plus 1, and think of those as transformations because they have the same effect on any function. So we'll do the arithmetic as far as we see here in terms of transformations. So we have our parent function. Let's get our x transformations. And we know the x transformations happen within the parent operation, which is the square operation. So I extract my x minus 3 from my transformed function here, and I treat it like it's in an equation that I'm trying to solve, like I'm trying to get x by itself, and the steps that it takes to get x by itself, in this case add 3, are my x transformations, okay? So I have one x transformation, and that is add 3. And I always like to say, since it's an x transformation, I make sure to say that that is 2x. So that is my one x transformation. Now the y transformations happen outside of the parent operation, outside of the square operation. So that is the 2 and the plus 1. And for those, I go in exactly the order that they're applied to the parent function, to the square. So the first thing that happens to the square is it multiplies by 2. And since it's a y transformation, I'll say multiply y by 2. Okay? And secondly, I'll add 1 to y. So you can see the difference between x transformations. You have to think about reversing the operations, and y transformations are exactly what you see. And when you have more than one x or y transformation, make sure you do these in the order that they occurred. We only have one x transformation, so we don't have anything to worry about there. And you can mix the x transformations into the y transformations if you like. Just make sure to do all the y transformations in the order that they're listed. Okay? So we have our parent function over here, and we've got our transformations. Let me kind of shift those off to the side now. We know what we're going to be doing. And let's start with our parent graph, for which I will choose 3 ordered pairs to represent it. We're already comfortable with this graph y equals x squared, and I'll roughly graph it here with 3 ordered pair representatives. So the one in the middle that I'll choose is when x is 0, y is 0 squared, which is 0. So I will use that point as our reference point in the middle, and then I'll choose a point where x is less than 0, such as negative 2, and I'll choose an x value bigger than 0, like 1. And if x is negative 2, y is negative 2 squared, which is 4, and 1 squared is 1. And now we've got our 3 ordered pairs, and this parent function looks roughly like this. It's a parabola going through the origin. And you can plot this more precisely if you want, but I don't think we need to. This is a very basic function. That's why it is one of our parent functions. And we're going to track it basically, and then we'll get a precise graph at the very end after we apply the 3 transformations. So the next thing I need to do is take this starting graph and do the transformations. So I will go and I will add 3 to my x values. I'm going to do this x transformation first. You can do the y's first if you want. So I'm going to write 3 plus all my x values. And I get a new set of ordered pairs. 3 plus negative 2 is 1, 3 plus 0 is 3, 3 plus 1 is 4. My y values don't change, and now my blue reference point is 3, 0 instead of 0, 0. And what happened was my graph moves to the right 3 units. That's what happens when you add 3 to x. So you can plot these points and see that, or you can just know it. So roughly it's going to look like this, the same shape, 3 units to the right with our reference point right here now. Sorry, trying to highlight here. There we go. Excellent. So we did this second. So we've got this transformation taken care of. Now let's do our y transformations. I need to multiply my y values by 2. So I'll put times 2 next to these y values. And I get a new set of ordered pairs. Let's go this direction. So 1, 3, and 4 are still my x values. My y values will be 8, 0, and 2. And our reference point is still 3, 0. What happens here is if you were to plot these points, 3, 0 didn't change, so it's still here, but 1, 4 becomes 1, 8, so it's twice as high, so the graph gets narrower in a vertical direction. We've got a vertical stretch. It's being stretched upright. So it's a vertical stretch. And it multiplied by 2, so we can say by a factor of 2, or just by 2. And our reference point is right here at 3, 0 still. So now we've got our first y transformation taken care of. Lastly, we need to add 1 to my y values. So I'll put plus 1 next to these y values. And we'll move that down here to get a new table of xy values. And by the way, I chose 3 representatives, 3 points to represent this graph, but you can certainly use as many as you want. 3 I'm doing in the interest of time. It's what I recommend to my students. Alright, so my x values didn't change, 1, 3, 4, but my y values are 9, 1, and 3. With our reference point now being the ordered pair 3, 1. And what happens here, when you add 1 to your y values, is your graph moves up 1 unit. So the reference point was 3, 0, now it's 3, 1, 1, 8, became 1, 9, 1 up, 1 higher, so it's still just as narrow as it was. It's just 1 unit higher than it was. So this is my final graph. Now I just need to make it look good and put it on a coordinate plane with more precision. So I'm going to take this guy and put it onto a coordinate plane. So now 1, 9 is up here, 3, 1, our reference point, is right here, and 4, 3 is right here. And now we get a better idea of how narrow this parabola is. Let me draw that a little better. Let's draw it this way. Something like this, and goes up forever, and our reference point is right here. So that is the graph of that original function, f of x equals 2 parentheses x, was it minus 3 squared plus 1. Let me double check that real quick. Okay, so that is the graph that we were looking for. And we can check this, by plugging in any ordered pairs. So these final ordered pairs make this equation true. And the original ordered pairs, by the way, these guys made the parent equation true. Okay, so make sure you understand that. Parent equation changes into this transformed equation as you do your transformations. So I never like to check my reference point. That's the easiest one. I like to check maybe the most bizarre point. So I'm going to check 1, 9. Does that make this true? In other words, x is 1, y is 9. So let's see. If I plug in to this equation, 9 for y, well that's f of x is y, so I get 9 equals 2 times parentheses, x is 1, so I plug in 1 for x, and I want to know, is this true? So let's see. So I get 9 equals 2 times 1 minus 3 is negative 2 squared plus 1. Negative 2 squared is 4, so I've got 2 times 4 plus 1. And 9 does equal 2 times 4 plus 1. So I'm pretty confident that this is the graph of this function. Okay? So you can start with your parent, do your transformations, and then you can check your answer by checking any of the ordered pairs that you've got, or all if you like. And that's how to graph a function using transformations.